Jnanam paramam dheyam. Knowledge is supreme.
Today we are going to discuss Einstein treatment. Well, when you take Einstein's name, what comes to your mind is relativity, and as you know, he got his Nobel Prize not for relativity but for photoelectric effect, right? So that is kind of the connection with this, because photoelectric effect also has to do with light. Today what we talk about is a rather simplistic approach that Einstein had developed, which enables us to, as you will see, correlate experimental and theoretical quantities eventually. Okay. So before we embark on that, let us remind ourselves what we have studied so far. First of all, we have studied that transition moment integral has to be non-zero, right? This has been said many times. What I'll do is, I'll just write this in a little different way today for the sake of brevity. This is our transition moment integral. Let's write it as mu Lm. Mu Lm, mod mu Lm, something like that. You'll see why. So what we have done so far is that we have arrived at this golden rule. What is this golden rule? What is there on the left hand side? dP L to m dt, right? Rate of change of probability, you can say. Okay, that is equal to 8. Please remind me, because I don't really remember expressions very well. 8 pi cube divided by 3h square multiplied by, we can write mu Lm mod square, anything else, into rho nu. What is rho nu? Rho nu is energy density, and let us see who can tell me the expression for energy density that we have from Planck's law. I remember the denominator, so I will write it. Denominator is e to the power h nu Lm. What is nu Lm? Nu Lm is the frequency that gives resonance for the energy gap that is there, divided by kT minus 1. This much I remember. In the numerator, if I remember correctly, there is an 8, there is a pi. What else is there? I think it is nu Lm cube divided by c cube, but I'll just check because I'm not all that good at writing. 8 pi h nu Lm cube divided by c cube divided by, whole thing divided by e to the power h nu Lm divided by kT minus 1. Okay, is that what I've written? Great, I'm proud of myself. Numerator? 8 by h nu. Yeah, h is what I had missed. So this is what we have. With this, we are sufficiently equipped to retrace the path of Einstein. What Einstein did was this. He considered the same two-level system that we were talking about. Lower level is L, upper level is N. Okay? Now, first of all, we trace two paths that we have discussed already. This arrow means what? Light has come in and has caused an induced absorption. Okay? For induced absorption, what should I write? B multiplied by rho nu. This whole thing is a constant, right? So Einstein wrote it as BLM. L is the level of origin, M is the destination level. So this is called Einstein's coefficient for induced absorption. Okay? This BLM is called Einstein coefficient of induced absorption. Okay? So this rate of transition for a single molecule from golden rule would be BLM multiplied by rho nu. Okay? What is the other process we have studied? Light comes, there is some excited state population here. This causes this to come down. This would be BML rho nu. What is BML? I think you can guess. It is Einstein coefficient for induced emission. Okay? In principle, you should be able to find out an expression for BML as well from this perturbation theory type of treatment that we have already done. But as you'll see, we don't need to. The answer that comes out is fairly simple. Now, this is the probability for one molecule. Now, if I consider that NL and NM are the populations of level L and level M respectively, then what can I do? If I just multiply this by NM, where NM is the number of molecules in M level, I multiply this by NL, which is the number of molecules in L level. Okay? What is that? That is, first you have the probability, that is for one molecule, then you multiply it by population. What do you get? See, this expression that we have, golden rule, that is dp dt, right? Probability. So that is for one molecule. I am multiplying it by population. What do I get then? You can think total number of transitions, right? Okay. Now, then Einstein induced something that was not there in our discussion so far. It is important to remember that light comes in and goes out as well. Okay? Einstein said there is always some spontaneous emission. And he said, let AML be this coefficient for spontaneous emission. Of course, he did not call it Einstein coefficient for spontaneous emission. Other people have added on his name to it. So AML is the coefficient of spontaneous emission, right? What do I have to multiply AML by this to get this rate of transition from M to L by the spontaneous emission pathway? Should I multiply by rho? Should I multiply by rho? What should I multiply by? NM, right? See, this, what do I write? Let me write S for system. S plus light forming A star, or maybe I can just write L and M. This is the first kind of, if you can think of, the first kind of reaction that we have, right? The other reaction, this one is M plus H nu forms L. The last one is essentially M forms L. I am not writing the plus H nu in the last two. So this you can think is a bimolecular reaction, this is a unimolecular reaction. So there is no scope of writing rho there, there is no need of writing rho there. Are we clear with this? Then we use something that we have studied in classes of chemical kinetics long ago. We use what is called steady state approximation. Before I write that, can you tell me what is steady state? What's the meaning of steady state? Or what is an example of steady state? Let me rephrase the question. What is the difference between a steady state and equilibrium? As chemists, we are all familiar with the term equilibrium, right? Chemical equilibrium. But chemical equilibrium and steady state are not one and the same. And perhaps you have studied long ago this example where you have this tank, right? Tap at the top, drain at the bottom, right? And the tap and the drain are adjusted in such a way that the level does not change. Is that a steady state or is that an equilibrium? It's a steady state. Why is it a steady state? Not really. When you talk about equilibrium, you mean a closed system. When you talk about steady state, you mean an open system. This system, as you see, is not really closed, right? Because light is coming from outside, light is going out. So it's an open system. But what you can think is, at steady state, rate of absorption should be equal to rate of emission. Okay? So at steady state, I can say that rate of population of M should be equal to rate of depopulation of M. Question? Okay, what is that process there? Absorption, right? So absorption, as I had written what I have erased now, absorption is like a reaction between molecule in the L state and light. Okay, so if I think of a rate of that reaction, rate of that process, so that should be a product of concentration of molecules in M state, that is Nm, number of molecules in M state, and concentration of light. So one way of writing concentration of light is energy density. I have written it wrongly, you are right. Achha. You are right. So, sorry if I confused you, it is NL here and LM here, of course. So you are right. Are we clear now or did it become more problematic? Yeah? Is it okay? Not okay? Yes or no? Yes. So again, please use that convention. This is not yes, this is no. Okay, so far? So at steady state, what will happen? At steady state, BLM multiplied by rho nu multiplied by NL should be equal to BML multiplied by rho nu multiplied by Nm plus AML multiplied by Nm. The rate of upward and downward transitions should be equal to each other. That's all. Now what will I do? See, I already know an expression for rho nu. Right? So if I try and rearrange that equation and make rho of nu the subject of formula, then perhaps I can compare the right hand side of that equation and the right hand side of Planck's law and get some information about how the A and the B's are related. Okay? That is essentially what we are trying to do. So let's try and do that. Rho nu multiplied by BLM NL minus BML NM is equal to AML NM. And hence I can write, I'll write here, if I make rho of nu the subject of formula, that should be equal to AML multiplied by NM divided by BLM NL minus BML NM. Okay? What am I doing? I am back calculating. Are we okay so far? Right? Now, what do I want? I want something like this. I want the second term to be minus 1. Minus is already there. I want to make it 1, so I'll just divide by I'll divide by BML NM. So if I do that, what do I get? AML divided by BML. This becomes 1. And what does this become? Divided by BML NM. Is it okay? Now we can use something else that we know already. Especially those of you who are studying that statistical thermodynamics course right now. Yes. I have 2 levels. Populations are NL by NM. You know very well what is NM by NL or what is NL by NM. What is NL by NM? To keep things simple, let us consider degeneracy to be 1. Actually, degeneracy also has a role to play here, but let's just put it to be equal to 1. What will NL by NM be equal to? Exponential NL by NM. NL by NM. NL is a lower level. So it is actually H nu Lm, right? Divided by KT. H nu Lm is the energy gap. NL is the lower level. That's why. Otherwise, if I wrote Nm divided by NL, it would have been e to the power minus H nu Lm by KT. That's all. And see, it's nice because here also I have e to the power H nu Lm. So I'll write it here. Minus 1 e to the power H nu Lm divided by KT. Now my job is done. What do I learn from here? First thing that I learned is that if you compare this expression with Planck's law, what do I learn? BLM by BML equal to 1. Is that right? First thing I learned is that BML equal to BLM. So since they are equal to each other, I don't have to bother about M and L. What is the order? I just write it as B. So Einstein coefficient of induced absorption is the same as Einstein coefficient of induced emission. This is a rather profound, very important result. Are we clear so far? What is the second thing that I learned? What is the second thing that I learned? Now I am not going to write M, L at all. I'll just write capital A and capital B. From the numerator you get capital A by capital B is equal to 8 pi H nu Lm cube divided by C cube. So we get a very convenient relationship between Einstein's A coefficient and B coefficient. Okay? And that again leads us to some very important result. First, in the treatment that we had performed earlier, did we consider spontaneous emission? The treatment that we did up to last class, did we consider spontaneous emission at all? We did not. What does Einstein treatment tell us? That spontaneous emission is always there. Okay? If B is there, see, if B is 0, let us say B is equal to 0, then A will be equal to 0, no problem. But then if B is equal to 0, that means transition between L and M is not even allowed. So if there is no absorption, what emission are we talking about? Okay? So it's important to understand that B tells me actually how allowed the transition is. So if B is 0, then only A is 0. If B is non-zero, A is also non-zero. So first thing that you learn is that you cannot ignore spontaneous emission. It is always there. Okay? Second thing that comes is, when does it become important and when is it not important? As you see, if I write like this here is the factor. And even within this is the only thing that can change depending on the system. 8 is a number, pi is a constant, H is a universal constant, C is a universal constant. Okay? let us see what this constant turns out to be. 8 into 3.142. Help me with the value of 8. 6.6 into 10 to the power minus 39 unit, 34 unit. Okay. What is C in that case? 3 into 10 to the power 8, not 10. Okay. So, what do I get here? 8 multiplied by 3.14 multiplied by 6.62 by 3. Oh, right. Who's going to, this is actually cube, right? Huh. What is the number? Can somebody calculate quickly and tell me? It should be approximately something like 20, right? Yeah? 8 by, oh no, not 20. Not 20. This is not 9, right? This is 27. 8 multiplied by 3.142 multiplied by 6.62 divided by 3 cube. What is 3 cube? 27. What is it? 5, 6, something like that, right? Yeah. Something. So, well, the point I am trying to make is 10 to the power 0. So, 6.1 multiplied by 10 to the power how much? 10 to the power minus 58. Actually, it's a very small number. Okay? But let us think what nu is. What is a typical value of nu for, say, microwave? What is the frequency of microwave? Frequency. Say 5 centimeter inverse. 10 centimeter? Well, microwave, right? So how much should it be? What is the frequency? So what did I say? 5 centimeter inverse. That is your nu bar. That is 1 by lambda, but in centimeter. Don't forget. So I want nu. What is the relationship between lambda and nu? Lambda nu equal to C, right? Wait, but let me work it out. Lambda nu equal to C is right. So your nu is basically C nu bar. Okay. So 3 into 10 to the power 10, if I do it in centimeter, multiplied by, we are saying 5 centimeter inverse. How much does it come to? Is it right? Is that in hertz? Right or wrong? Right. So it is 15 into 10 to the power 10. I'll take that 15 to be 10, so 10 to the power 11 or something like that. So 10 to the power 11 cube, how much is that? 33. Right? 10 to the power 11 is 33. So minus 58 plus 33, that's a very small number. What does that mean? That means in microwave regime, you have very little spontaneous emission. Right? So microwave, spontaneous emission is not too much. So if you look at emission in microwave, it is predominantly stimulated emission. Contribution of spontaneous emission, as we said, can never say it is 0, but it is very small. Let us go to UV. UV vis. That is, I remember this nu bar is 10 to the power 5. 5 or 4, 10 to the power 4 actually. Right? 10,000. 10,000, 20,000, that is your basically UV visible region, right? 18,000 is red, I think, and 24,000 or something is blue. So basically 10 to the power 4. So if this is 10 to the power 4, your nu bar, then what is nu? Then nu will be 3 into 10 to the power 10 into 10 to the power 4, that becomes 10 to the power 14. Cube of that, how much is it? 42. Now see, 58 minus 42. Well, much better than microwave. Much better than microwave, right? And in fact, that is a problem. What we realize is that as the energy gap increases, contribution of spontaneous emission also increases compared to stimulated emission. That is a problem when you want some application that is based on stimulated emission. And the application that is most relevant to spectroscopy is laser. We are going to discuss lasers from next class onwards. So when you want to make a laser, you want to amplify the stimulated emission. And at that time, you do not want depopulation of the excited state to take place by spontaneous emission. So it turns out that it is very easy to make a laser in microwave. In fact, the first laser that was invented was a maser. Maser means microwave amplification by stimulated emission of radiation. And till date, a UV laser remains elusive. We do not have a laser that gives you ultraviolet light directly. You do get ultraviolet laser light, but invariably that is infrared or maybe visible photons which are added up to give you a higher energy. We'll talk about it a little more when we discuss lasers next day, not today. But for today, until now, the message that we have is this. We have discussed Einstein's kinetic treatment of this two-level problem, and we have learned two things. Einstein coefficient for absorption is equal to the Einstein coefficient of stimulated emission. Number two, we have learned that your spontaneous emission is never zero. A can never be zero if B is non-zero. But A makes a relatively higher contribution when the energy gap is higher, when frequency is higher. It makes a relatively lower contribution when the energy gap is lower, frequency is lower. And that has profound implications on applications based on stimulated emission. Okay, that is the end of this part of the discussion.